The Laplace transform of the sinusoid function, sine omega t, is one of the trickier table building exercises that we'll do. And that's just because of the nature of how we have to do the integration. The definition is exactly the same as before. So the Laplace transform capital F of s is equal to the integral of 0 to infinity of the function sine omega t times e to the minus st dt. And so our technique that we'll use here is integration by parts. So if we define our u function as sine omega t, then the derivative of that is omega cosine omega t dt. And if we define the dv function as e to the minus st dt, then the integral of that, we get v is equal to minus 1 over s e to the minus st. Plugging that into the integration by parts formula, u times v evaluated at the definite integration limits minus the integral of v du, and we just plug in the definitions we just calculated, then we get minus 1 over s sine omega t e to the minus st evaluated by those limits. And so at those limits, at infinity, the exponential is 0, and at 0, the sinusoid function is 0. And so in that case, we just get 0. And then we are left to evaluate the integral. And so again, we're stuck at the same point, and so we need to do the integration by parts one more time. If you remember the way that you might have done sine squared, using the integral of just sine squared back when you're doing calculus, integration by parts, this is exactly what we're doing here. So we do integration by parts again, making the same definitions for u and dv. And so we plug that again into the formula for integration by parts. This time, cosine at 0 is 1, and so we evaluate one of the terms, becomes that minus 1 over s in the green there. And then the important part here, the trick is to notice that in the integral, once we've done integration by parts twice, in that integral, in orange, is actually the same thing that we started with. And so that's what we're trying to find. So if the left-hand side is equal to the capital F of s, the Laplace transform of the function, then on the right-hand side, now we have a term that is also capital F of s. And so if we rewrite that, we just have F of s is equal to omega over s squared minus omega squared over s squared times F of s again. And so if we combine F of s and we solve for it, we get the Laplace transform of the sinusoid function is omega over sine squared plus omega squared. Now, there is an easier way of solving for this Laplace transform, and that's using the Euler identity for the sine function. So using Euler, we can rewrite sine as in terms of two exponentials. And so this is often a very handy way of dealing with sinusoids. You get rid of all of the trig and you're just left with exponentials, which are much easier to integrate and differentiate. And so if we do that, we plug this definition into our Laplace transform, then we have two exponential functions, and these are relatively straightforward to integrate, and we get the exact same answer. One of the things we'll learn in class is that the Laplace transform is linear, and that would actually make solving this integral even easier, because then we could just say that the Laplace transform of the sinusoid is just the Laplace transform of the positive exponential e to the I omega t minus the Laplace transform of the negative exponential e to the minus I omega t. And you'll see at the end, that's actually what we find. We'll conduct a few more examples in class where we also use integration by parts to give you some more practice.